Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on electrochemistry. Let's go ahead and get started with problem number 1. Problem number 1 says rusting occurs due to the oxidation-reduction reaction of iron with environmental oxygen, and we're given the reaction here. Now some metals, they cannot react with oxygen in this fashion. Which of the following best explains why iron can? Now, the first thing we want to do is take a closer look at this reaction. Taking a closer look, we can begin to assign oxidation numbers, and here we notice that iron loses electrons and it is oxidized, and oxygen gains electrons and it is reduced. Now, the ability of a metal to undergo oxidation or reduction is characterized by its reduction potential. Reduction potential is a measure of the tendency of a chemical species to acquire electrons and be reduced. Metals with more positive reduction potentials are more likely to gain electrons and be reduced, while those with more negative reduction potentials are more likely to lose electrons and be oxidized. Now, keeping that in mind, let's work through each of these answer choices and analyze it to determine if it is correct or incorrect. Option A says iron has more positive reduction potential than those metals, making it more likely to donate electrons to oxygen. This statement is incorrect because a more positive reduction potential means that a chemical species is more likely to gain electrons and be reduced, not donate them and be oxidized. So option A is incorrect. What about option B? Option B says iron has a more positive reduction potential than those metals, making it more likely to accept electrons from oxygen. Now, this option is incorrect because in the context of rusting, iron needs to lose electrons and be oxidized, not accept them and be reduced. So option B is also incorrect. Option C says iron has less positive reduction potential than those metals, making it more likely to donate electrons to oxygen. Now, this statement is correct. A less positive or more negative reduction potential means that iron is more likely to lose electrons and be oxidized. Thus, iron can donate electrons to oxygen during the rusting process. Option C is the correct answer, but let's work through option D as well. Option D says iron has less positive reduction potential than those metals, making it more likely to accept electrons from oxygen. Now, this statement is incorrect because it contradicts the process of rusting, where iron donates electrons and is oxidized rather than accepting them. And so, the correct answer for problem 1 is C. Let's go ahead and move into problem 2. Problem 2 says, given the following standard reduction potentials, what is the standard electromotive force of the following reaction? Now, the standard reduction potential of a half reaction, it measures the tendency of a species to gain electrons and be reduced. The more positive the reduction potential, the greater the tendency to be reduced. Now, to find the standard electromotive force for this reaction, we need to combine the reduction potentials of the two half reactions. But first, we need to identify which half reaction will be the oxidation reaction and which will be the reduction reaction. In this given reaction, zinc is being reduced and silver is being oxidized. So in other words, the cathode is zinc because it is being reduced, and the anode is silver because it is being oxidized. Now, to determine the standard electromotive force of a cell, we simply subtract the standard reduction potentials of the two electrodes. So this is going to be negative 0.763 volts minus 0.337 volts. This gives us negative 1.1 volts. And that means that the correct answer is going to be B. One side note. While we need to multiply the silver half reaction by 2 to balance the electrons, the actual value for the reduction potential does not change. This was something we talked about and emphasized on in lecture. Remember that the standard reduction potential is determined by the identity of the electrode and not the amount of it present. So again, the correct answer to problem 2 is answer choice B. Next up, we have problem 3. Problem 3 says, consider the following data. The anode of a certain galvanic cell is composed of copper. Which of the metals from the data table can be used at the cathode, assuming equal concentrations of the two electrolyte solutions? Now, to determine which metal can be used as the cathode in a galvanic cell with a copper anode, we need to understand how a galvanic cell works and the significance of reduction potentials. So in a galvanic cell, the anode is where oxidation occurs, loss of electrons, and the cathode is where reduction occurs. This is the gain of electrons. And this cell, it generates electrical energy from a spontaneous redox reaction. Now, the standard reduction potential, this is a measure of the tendency of a chemical species to gain electrons and be reduced. And we said this earlier, but the more positive the reduction potential, the greater the tendency to be reduced. Now here in this galvanic cell, we're told that the anode is made out of copper, and that means that the anode is going to be oxidized. For a spontaneous reaction in a galvanic cell, the overall cell potential must be positive. This means that the reduction potential of the cathode material must be more positive than the oxidation potential of the anode material. Since the anode is copper with an oxidation potential of 0.52 volts, the cathode needs to be a reduction potential that is greater than that to ensure a positive cell potential. So considering that, the correct answer has to be A, mercury, because it is the only one that has a reduction potential greater than 0.52 volts. Its reduction potential is 0.85 volts. And so the correct answer to problem 3 is A. Beautiful. Let's move on to problem 4. Problem 4 says an electrolytic cell is filled with water. Which of the following will move toward the cathode of such a cell? Statement 1 says hydrogen ions, Statement 2 says oxygen ions, and Statement 3 says electrons. Now, in an electrolytic cell, ionic compounds are broken into their constituent ions. The positively charged ions or cations migrate towards the cathode, which is the negative electrode where reduction occurs. And the negatively charged ions or the anions, they migrate toward the anode, which is the positive electrode where oxidation occurs. Now, given the situation described in this problem, we need to determine which species will move toward the cathode. Now, in this case, the cations are hydrogen ions, so option 1 is correct. In addition, electrons flow from the anode to the cathode in all types of cells, meaning that option 3 is also correct. But option 2 is incorrect for two main reasons. First, it's unlikely that the anions in any cell would be O2- rather than hydroxide ions. And second, these anions would flow to the anode, not the cathode. So that is why option 2 is incorrect. The only true statements are 1 and 3, which makes the correct answer for problem 4 answer choice C. Next up, we have problem 5. Problem 5 says if the value of the standard EMF of the cell is known, what other data is needed to calculate the standard Gibbs free energy change? Now, in lecture, we discussed this very important equation here that relates the standard cell potential to the standard Gibbs free energy change. Here, we have that the standard Gibbs free energy change is equal to negative N, where N is the number of moles of electrons transferred in the redox reaction. It's multiplied by F. F is Faraday's constant. It's approximately 96,485 coulombs per mole of electrons. And then that's multiplied by the standard cell potential. If we're given E cell, what other data do we need to calculate the standard Gibbs free energy change? Well, F is a constant, so we don't necessarily need any information about that. It's a constant, we know the value, but what we do need to figure out is N. We need to figure out the number of moles of electrons that are transferred in the redox reaction. Now, looking at our answer choices, A says equilibrium constant, B says reaction quotient, C says temperature of the system, D says half reactions of the cells. Here, option D is exactly what we need to figure out N if we want to use this equation. The half reactions, they provide the information about the number of moles of electrons that are transferred in the overall redox reaction. So we need that in order to be able to calculate standard Gibbs free energy change if we already have the standard cell potential. N would be the only other variable we would need to figure out. So the correct answer for problem 5 is going to be D. Beautiful. Next, we have problem 6. Problem 6 asks, which of the following compounds is least likely to be found in the salt bridge of a galvanic cell? Now, a galvanic cell generates electrical energy from a spontaneous redox reaction. It consists of 2 half cells, each containing an electrode and an electrolyte solution. The salt bridge is a crucial component that maintains electrical neutrality by allowing the flow of ions between the half cells. Now, a good salt bridge typically contains a strong electrolyte that dissociates completely into ions, and this ensures efficient ionic conductivity. Now, we have 4 options here: sodium chloride, sulfur trioxide, magnesium sulfite, and ammonium nitrate. When we're looking at these 4 options, we want to determine which one of these is going to be least likely to be found in the salt bridge of a galvanic cell. In other words, we're looking at which one of these options is not going to dissociate and is not a strong electrolyte. Now, A, C, and D are known to be strong electrolytes because they completely dissociate in solution. But B, sulfur trioxide, this is not an electrolyte because its atoms are covalently bonded, so it will not dissociate in aqueous solution, which means the correct answer to problem 6 is going to be B. Let's tackle problem 7. Problem 7 says if the surface area of an electrode material in an electrochemical cell is tripled, what else is necessarily tripled? Statement 1 says our standard cell potential, statement 2 says current, and statement 3 says our equilibrium constant. Let's go over each of these one by one and see what is going to change when our surface area is tripled. Standard cell potential. This is determined by the intrinsic properties of the materials involved in the redox reaction and their standard reduction potentials. It is not dependent on the physical size or the surface area of the electrodes. Therefore, increasing the surface area will not change the standard cell potential. What about current? Current is in an electrochemical cell is directly proportional to the surface area of the electrodes. A larger surface area actually allows more electrons to be transferred per unit time, thereby increasing the current. That means tripling the surface area of the electrodes will consequently triple the current, assuming other factors like concentration and voltage remain constant. So statement 2 is correct. This will be tripled if the surface area is tripled. What about equilibrium constant? The equilibrium constant is related to the Gibbs free energy change of the reaction, which in turn depends on the standard cell potential. Since the equilibrium constant is derived from thermodynamic properties and not from physical dimensions, changing the surface area is not going to affect the equilibrium constant. So the only thing that will be affected by tripling the surface area is going to be current, which is statement 2. The correct answer for problem 7 is going to be B. Let's do problem 8 now. Problem 8 says, which of the following can alter the electromotive force of an electrochemical cell? Now, the EMF of an electrochemical cell, also known as the cell potential, is primarily determined by the standard reduction potentials of the half reactions occurring at the electrodes. Keeping that in mind, let's work through each answer choice. Option A says the mass of the electrodes. This option is incorrect because the mass does not affect the EMF. The EMF is determined by the nature of the redox reactions and their reduction potentials, and not by the amount of electrode material that's present. So A is not true. Option B says the length of the wire connecting the half cells. This option is also incorrect because the length of the wire affects resistance and current, but not the electromotive force. So B is not true. C says the overall size of the battery. Again, this option is incorrect because the size of the battery does not influence the EMF. The electromotive force depends on the chemical nature of the reactions and not on the physical dimensions of the cell components. So we can cancel out option C as well. Option D says the temperature of the solutions in the half cells. Now, this option is correct because temperature can alter the electromotive force as described by the Nernst equation, which includes a temperature term. Now, according to the Nernst equation, the EMF of an electrochemical cell is temperature dependent. So increasing the temperature can change the reaction kinetics and the equilibrium position, thereby altering the electromotive force. So the correct answer to problem 8 is going to be answer choice D. Wonderful. Problem 9 is next. It says, which of the following statements could be true about a sodium-cadmium cell based on the information below? Answer choice A says it is a galvanic cell and sodium is the cathode. B says it is an electrolytic cell and cadmium is the anode. C says it is a galvanic cell with the standard EMF equal to 3.11 volts. And D says it's an electrolytic cell with the EMF, the standard EMF, equaling negative 3.11 volts. So let's work through this. In a galvanic cell, all right, the galvanic cell generates electrical energy from spontaneous redox reactions. Here, the species with the higher reduction potential will be reduced at the cathode, and the species with the lower or the more negative reduction potential will be oxidized at the anode. For a sodium-cadmium cell, cadmium has a less negative reduction potential compared to sodium, hence cadmium would be reduced in the cathode and sodium will be oxidized at the anode. So then we can go ahead and based off of that, eliminate answer choice A because A says it's a galvanic cell and sodium is at the cathode. This is incorrect. Cadmium is going to be reduced. It's going to be at the cathode. Now, in addition here, the cell potential for a galvanic cell is going to be negative 0.4 volts minus negative 2.71 volts. That gives us 2.31 volts. All right, positive 2.31 volts for a galvanic cell. Knowing that, we can again eliminate answer choice C. All right, then let's work through an electrolytic cell. Remember, an electrolytic cell, it requires external electrical energy to drive a non-spontaneous redox reaction. The direction of electron flow is going to be reversed compared to a galvanic cell. So if the sodium-cadmium cell is an electrolytic cell, sodium would be reduced, it'd be the cathode, and cadmium would be oxidized, it'd be the anode. And that matches up with answer choice B. It is an electrolytic cell, and cadmium is the anode because it would be oxidized. So option B is correct, and actually it is the correct answer for this problem, but I want to show you why answer choice D is incorrect. For an electrolytic cell, all right, the cell potential would be calculated as negative 2.71 volts minus negative 0.4 volts. That would give us negative 2.31 volts, which doesn't match with the number that's given in answer choice D. So that means the correct answer for problem 9 is going to be B. Let's tackle problem 10. Problem 10 says, which of the following expressions correctly describes the relationship between standard electromotive force and standard change in free energy? Now, there are only two equations involving change in free energy in electrochemical cells. The first one says that the standard change in Gibbs free energy is equal to minus N, where N is the number of moles of electrons exchanged, multiplied by F, which is Faraday's constant, multiplied by the standard EMF of the cell. Now, the EMF of a reaction is determined by calculating the difference in reduction potentials between the two half cells. So it can be written in the following manner, where we have the cathode minus the anode. We can take this expression right here and plug it back into our equation. If we plug in this definition into our equation and then distribute the negative sign here, we would get answer choice D, which is the correct answer for problem 10. Answer choice A is incorrect because it misrepresents how we calculate the EMF of a reaction. Now, let me also explain why answer choices B and C are incorrect. So another expression for the standard change in free energy says that it is equal to minus RT, R is the ideal gas constant, T is temperature, multiplied by the natural logarithm of our equilibrium constant. Now, if we take this expression and set them equal to each other, since they both equal the standard change in free energy, we would get the following equation. Now, if we take this and we want to redefine it so that we have on one side the standard EMF of the cell and then all the other variables to the other side, we would get the following equation. The standard EMF of the cell is equal to RT over NF multiplied by the natural logarithm of the equilibrium constant. Neither one of these expressions matches this, so they are also incorrect. With that, the correct answer to problem 10 is D. Let's move on to problem 11. Problem 11 asks, which of the following choices is indicative of a spontaneous reaction, assuming standard conditions? A says that the standard cell potential is negative. Now, this is incorrect because a negative standard cell potential indicates a non-spontaneous reaction under standard conditions. If instead this answer choice said that the standard cell potential was positive, then that indeed would indicate a spontaneous reaction under standard conditions. And this is because a positive standard cell potential corresponds to a negative Gibbs free energy change, which signifies spontaneity. So answer choice A is incorrect because it says negative instead of positive. B says that the reaction quotient is equal to the equilibrium constant. Now, at standard conditions, the reaction quotient equals the equilibrium constant at equilibrium. However, this alone does not indicate spontaneity without any additional context. So answer choice B is not correct either. Answer choice C says that the cell is a concentration cell. Now, this does not inherently indicate spontaneity under standard conditions. It depends on the specific concentrations involved. So that is the caveat. Yes, concentration cells can be spontaneous. However, if the concentration cell, for example, has reached equilibrium, it would actually cease to be a spontaneous reaction. So it depends where the reaction is at. It depends on specific concentrations involved, etc. So C is also not the correct answer. Answer choice D says that the equilibrium constant is greater than 1. Now, when your equilibrium constant is greater than 1, it indicates that the products are favored at equilibrium, suggesting that the reaction is spontaneous under standard conditions. So this answer choice is correct. Answer choice D. Wonderful. Let's move on to problem 12. This is a typo. This is problem 12, but I have written 13. We're going to move on from that. This problem says, for a cell with the following half reactions, and here we have the anode and the cathode reactions, how would decreasing the pH of the solution inside the cell affect the electromotive force? A change in pH has a direct correlation to the hydrogen ion concentration. Now, decreasing the pH increases the hydrogen ion concentration, which means the concentration of products has increased in the oxidation of sulfur dioxide. This means it would be harder to liberate electrons, thus decreasing the electromotive force. So the correct answer to problem 12 is going to be answer choice A. Beautiful. Let's tackle problem 13. Problem 13 says an electrolytic cell necessarily has blank. A says that the entropy is greater than 0. B says that the Gibbs free energy is less than 0. C says that the equilibrium constant is less than 1. And D says that the standard EMF of the cell is greater than 0. Now, an electrolytic cell is non-spontaneous. And so that means the delta G, the change in Gibbs free energy, has to be positive, and the standard EMF of the cell must be negative. Keeping that in mind, we can quickly eliminate B and D because they have the opposite trends for Gibbs free energy and the standard EMF of the cell. Now, what about delta S? What can we say about the change in entropy for an electrolytic cell? The change in entropy, it could be positive or negative. It really depends on the species involved. So we can't say that for an electrolytic cell, delta S, the change in Gibbs free energy, is always greater than 0. And for that reason, we need to eliminate answer choice A. Now we're left with answer choice C. This is the correct answer. The equilibrium constant is less than 1. Why is this true? Well, the answer lies in this equation where the change in standard free energy is equal to minus RT, where R is the ideal gas constant, T is temperature, and that's multiplied by the natural logarithm of the equilibrium constant. If the equilibrium constant, KEQ, is less than 1, then this would result in this whole term being less than 0, which means delta G is going to be positive, which is what we want because an electrolytic cell is non-spontaneous. So delta G needs to be positive. And if KEQ, the equilibrium constant, is less than 1, then that is going to be true. So the correct answer for problem 13 is C. Let's move on to problem 14. Problem 14 asks, which of the following is the best explanation for the fact that a larger mass of electrodes are required for lead-acid batteries as compared to other batteries to produce a certain current? Before we go through our answer choices and discuss which one is correct and which one is incorrect, I want to go over a couple of concepts. First, energy density. Energy density refers to the amount of energy that's stored in a given system or a region of space per unit volume or mass. This is a really important concept when we discuss batteries. Batteries with higher energy density, they can store more energy per unit mass, which means they require less material to produce the same amount of energy. On the other hand, batteries with lower energy density, they require more material to store the same amount of energy. Now, lead-acid batteries, they're known for their relatively low energy density compared to other types of batteries like lithium-ion batteries. This low energy density means that lead-acid batteries require more material, larger mass of electrodes to store and deliver the same amount of energy. Now let's go over the answer choices and evaluate each option. Answer choice A says the lead-acid electrolyte, sulfuric acid, is diprotic and incompletely dissociates in solution. Now, this statement about sulfuric acid being diprotic and its dissociation is true, but it's not directly related to the need for a larger mass of electrodes. The dissociation of the electrolyte does not significantly affect the mass of the electrodes required. So answer choice A is really not a good answer. What about B? B says the energy density of lead-acid electrodes is higher than that of other batteries. This is incorrect. The energy density of lead-acid batteries is actually lower than that of many other types of batteries. So B is also incorrect. C says the electrolytes in other batteries less readily dissociate than those of lead-acid batteries. This statement does not address the key issue of energy density and the mass of electrodes. The dissociation of electrolytes does not directly relate to the mass of electrodes that are needed. So answer choice C is also incorrect. D says that the energy density of lead-acid electrodes is lower than that of other batteries. This is the correct explanation. The lower energy density of lead-acid batteries means they need more material to store the same amount of energy, and so they require a larger mass of electrodes. The correct answer for problem 14 is answer choice D. And with that, we can move into our last and final problem, problem 15. Problem 15 asks, which of the following best describes why overcharging a nickel-cadmium battery is not detrimental? A says the energy density of a nickel-cadmium battery is high, so it can store more charge than other batteries per its mass. B says the electrodes of a nickel-cadmium battery can discharge through the circuit when they are fully charged. C says the nickel-cadmium battery will stop accepting electrons from an outside source when its electrodes are recharged. And D says nickel-cadmium batteries have a high surge current and they can dissipate the overcharge before damage can occur to electrodes. Now, nickel-cadmium batteries are rechargeable cells, and they consist of two half cells made out of solid cadmium, which is the anode, and nickel-3 oxide hydroxide, which is the cathode. And they're connected by a conductive material, typically something like potassium hydroxide. Now, during the recharge cycle, nickel-cadmium cells are going to accept current from an outside source until the cadmium and the nickel-3 oxide hydroxide electrodes are pure. At this point, the reaction is going to stop because cadmium hydroxide runs out and no more electrons can be accepted. Now, answer choice A and B are both true statements, but they fail to explain why overcharging the battery is not a problem with nickel-cadmium batteries. Answer choice C is correct. It's going to stop accepting electrons from an outside source when its electrodes are recharged. This is why overcharging the nickel-cadmium battery is not detrimental. Now, D talks about something regarding surge current. Surge current refers to the initial burst of current that's seen in some batteries. Once charged, the surge current is not going to increase even if the power source continues to run, because no additional charge is going to be stored on the electrodes. This doesn't explain what we're being asked in this problem, so this is incorrect as well. The correct answer for problem 15 is going to be answer choice C. And with that, we've completed this practice problem set. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.